Good afternoon, everyone. Today's lesson is going to be on Pascal's triangle, and the main application is going to have to do with polynomials. But to show you where it comes from originally, this is a problem that if you decide to take data management, you would do something like this during the class. It has to do with counting things. So here's the kind of problem would be: these 9 little gray squares are 9 desks. So suppose there's a student in the back corner, right, sitting here, and he wants to ask me a question. Okay, and I am currently standing over here, okay, and I'm going to walk over to that student to help them. Okay, how many different ways can I do that, or how many different paths are there to get over to that location? Okay, so the way we do this is just by considering, first, I'm only going to walk either to the right, or I'm going to walk straight down, okay, because otherwise I'd be backtracking and it wouldn't be helpful. So now I'm going to consider how many ways I can get to the different corners. So that first arrow I drew at the top, right, there's exactly one way I can get to this location, okay, because I can just walk from here to here, and that's pretty much it. Okay, if I keep doing that, okay, there's only one way to get to this corner of the room and one way to get to that corner of the room. Okay, similarly, if I go down this side, okay, there's one way to get to this corner, one way to this corner, and one way to get behind the back row of the desk there. Okay. So what about some of the middle spots? What about this location right here? Well, I either could have come across the top first and then down, right? Or I could have come this way and then across that way. So there would be 2 ways I can get to that location. And so I'll go 2 here. Okay. Another way, though, I can think of that is looking at the way the previous corners. Right? Either I came from here, there was one way to come from there, or I came from here, there was one way. So 1 plus 1 gives me the 2. And if I go to that next location over here, how many ways? Well, there were 2 ways to come from here, because there were 2 ways to get to the previous corner. There was one way from there, so that totals 3. Okay, for the next one, okay, this totals 4. And I just continue this reasoning as I go through my little map here. Okay, this corner down here, there's one way to come from the left. Okay, 2 ways to come from above, so that's also a 3. For my next corner, I have 3 from this way, 3 from this way. That's a total of 6. Okay, next one, 6 and 4 makes 10. Okay, and we'll do that one more time. 3 plus 1 is 4. 6 plus 4 is 10. 10 plus 10 is 20. So there are 20 different routes I could take to answer the student's question. Or another thing that might be, if the student asked me 20 questions, I could walk a different way to get from one corner to the other, and could do that for every question. Okay, now the only thing I need to do a little adjustment here on is back at the start, I have a little circle. It looks like it's a 0 for where I was standing. Okay, we'd also call that a 1 in this model, right? There's one starting position. I can only start there, and then I go from there. Okay, Pascal's triangle basically looks like this, but tilted on its side. So here's how you develop and write down your own version of the triangle. Okay, we basically just taking that diagram and tilting it. So the top row is a 1. So I write down a 1. Okay, if I'm expanding on my diagonals, so my next row is also going to be 1, 1. Because when I go diagonally, that was like our corners, I get 1s. Okay, I'll write it out again for my third row. Okay, what do I do with the blank space in the middle? Well, I take the 2 numbers that were above it on the left and right. Okay, so those middle numbers are found by adding the 2 numbers diagonally above. So my middle number is going to be a 2. Okay, for my next row, same idea. First number is a 1. Okay, next one, I have a 1 and a 2, so that totals up to 3. 2 plus 1 totals up to 3, and then 1. And we can keep this pattern going. Okay, my next row would be a 1, followed by a 4. 3 plus 3 is 6. 3 plus 1 is 4. 4 plus 1. Sorry, not 4 plus 1. The outside is a diagonal. There's no number over here. Okay, we'll do one more. Row 5. Okay, 1 plus 4 is 5, 4 plus 6 is 10, 10, 5, and 1. Okay, and so on. Okay, you can keep expanding this thing as much as you would like, and the rows just keep going and going. Okay, so that's how you develop the triangle. Okay, and if you want to see a whole bunch of rows, go into Google, type Pascal's triangle. I'm sure you can find a diagram that has 13, 14, lots and lots of rows, and you can see how quickly the numbers build up. Okay, there are lots of other patterns here. We're not going to get into that too much in this course, but for example, you can see that when you look at a row of the triangle, okay, I apologize for a second. My thing crashed, so this would have jumped a little bit there. But yeah, when you're looking at a row, you can notice as you go from one side to the other, right, it repeats itself, right? It goes 1, 5, 10, but then goes back down 5, 10, 5, 1. Right? So the rows are palindromes. There's lots of different patterns you can play with. Like you could try adding up a row and see what it equals to. You could alternate, add, subtract. What happens when you do add, subtract, and so on across the row. Like there's different patterns you can play with. The application in this course is using it with binomials, and that might not seem to make a lot of sense, but we'll show what's going on here. So to see what's going on, we're just going to do a little expansion thing here. So here are some binomials, and we're going to review how to expand those out. Okay, although the first one, okay, x plus y to the power of 0 is kind of a cheap one. Okay, right, anything to the power of 0 is 1. Okay, so that's going to be a 1. Okay, x plus y over 1. And, well, that's going to be itself, so it is x plus y. Okay. To do x plus y squared, okay, we have to remember what that means, right? It means x plus y times another x plus y. Okay, so when I FOIL that out, right, I'm going to get an x squared. Okay, I'm going to get an xy and another xy. So I have 2xy. Okay, and then when I do the last one, I get y squared. Okay, the last one is x plus y to the power of 3. Okay, so this one's going to take a little bit of work. So I'm going to write down the brackets, and we'll do it on the side here. Okay, and again, just a reminder to whoever's watching the video, please feel free to pause, rewind as you need to make sure everyone gets the note down. All right, so this means I have x plus y, and I have it 3 times. Okay, so now we just did what happens when I multiply 2 of them together, right? X plus y squared. So if I multiply the first 2 together, I get my x squared plus 2xy plus y squared, and that's going to be times x plus y. Okay. And now I need to expand that out. So I've got x squared times x, that's x cubed. Okay, now x squared times y is x squared y, but then 2x y times x is 2x squared y. So that's going to be a grand total. Actually, I'll just write them all out first. So I got an x squared y and got a 2x squared y. Okay, my next pair of terms are going to be 2xy squared and xy squared. And then finally, a y cubed is my last term. So in total, I have x cubed plus 3 x squared y plus 3 xy squared plus y cubed. Okay, and I'll go put that back up at our summary. So this equals x cubed plus 3x squared y plus 3xy squared plus y cubed. Okay, so having a peek back up here, here's what I've got so far with my powers. Okay, I had a 1, I had an x and a y, okay, and we don't normally write them down, but just for the sake of argument, right, we'll write the coefficients there, right? That is 1x and 1y. Okay, my next row, I have 1x squared plus 2xy. plus 1y. And my next row, I have 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. Okay, and hey, look, okay, those numbers, right? I have a 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Okay, those coefficients in that expression are the exact same thing as what's in Pascal's triangle, right? These are the different rows, 1, 1, 1, 1, 2, 1, and so on. So if I wanted to do a little bit of a jump, okay, and do x plus y to the power 5, okay, I don't really need to sit there and write out all of those brackets. Okay, I can just think about what's going on and start writing it out. Okay, so it's row 5. So I'm going to go back to Pascal's triangle and grab the row that has the 5 in it because it was 5th degree. So these numbers, 1, 5, 10, 10, 5, 1, those are going to be my leading coefficients in that expression. Okay, so my first one's going to be a 1. Okay, what's happening with the powers, right? I have x and y. Well, let's go back to power 3. Okay, what's happening with x, right? In the first term, it's x cubed, and the next one is x squared. Then it's just x, which is x to the 1, and it disappears. So it looks like that's counting down. Okay, for y, okay, it's not in the first term, but then it's a 1, and then it's a squared, and then it's power 3. So those powers are counting up. Okay, so to start running this through, okay, that'd be 1, x to the 5th. And just for completeness, I'm going to write y to the 0 because there wasn't a y there. Okay, the next number in the row from Pascal's triangle was a 5. Okay, my power of x drops 1, x to the 4, and the y goes up 1. It's 1. Okay, next one is 10. X goes down, x cubed. Y goes up, x squared. And now we just continue this pattern. Okay, plus 10, x to the 4. Oh, pardon me, not x to the 4. X is still counting down. Okay, x squared, y goes up, y cubed. Plus 5, x keeps going down, so x to the 1. Y to the power 4. And my last term is 1, x to the 0, because x is going to disappear there, and y to the 5. Okay, so now I'm just going to write a little cleanup step, okay, just getting rid of the stuff we don't have to write down. So this is x to the 5, right, y to the 0 goes away, 5x4y plus 10 x cubed y squared plus 10 x squared y cubed plus 5 xy4 plus y to the power 5. Okay, done. So I did a power 5 expansion in like 2 lines just by using the pattern, and it connects to Pascal's triangle. Okay. If you take data management next year or the year after, you'll see a little more deeply why this pattern is connected like this. Okay, but that's how it works. So we're going to do one more example with a slightly more complicated expression. Okay, but here's again the summary of what happens. Okay, right? The coefficients, okay, are from the nth row of Pascal's triangle. Now there's a little bit of a catch there. In Pascal's triangle, okay, we're going to call that first row 0 to correspond to that 0 power in the expansion. This is going to be row 1. This is going to be row 2. This is my first row, second row, etc. Okay, so there's just a little catch about this. But yeah, basically, you look for the row where the second number is the same as your degree. Okay, whatever the first term in your expansion is, starts at the highest possible power and it counts down. Okay, the other term starts at the lowest possible degree and counts up. So to show with a slightly more complicated thing, we're going to expand this out. Okay, 2x minus 3 to the power of 4. Okay, so a couple things to note. Okay, so my first term is going to be 2x. My second term is going to be negative 3. I have to account for that negative. Okay, my exponent is 4, so that means I need the row of Pascal's triangle that has a 4 in it. So I'll keep writing out the rows. 1, 3, 3, 1, 1, 4, 6, 4, 1. So this is the row that I need because it is degree 4. So now we'll start writing out what the expansion looks like. So my first number, my coefficient is a 1 from Pascal's triangle. My next term is a 2x, and that is all to the power 4. Okay, my third thing is a negative 3, and that's to the power 0. Next term. Okay, the next number from the row of Pascal's triangle is a 4. Okay, my first term to the x, all to the power 3. Okay, negative 3 to the power of 1. Okay, next thing in Pascal's triangle is a 6. Okay, and then 2x all squared, negative 3 all squared. Okay, and again, we just keep writing this out. So plus 4, 2x to the power of 1, negative 3 cubed, plus 1, 2x to the 0, negative 3 to the power of 4. Okay. Next step is going to be to tidy up all those brackets. Okay, so from the first block, okay, I'm going to leave my 1 alone for a second there. Okay, next piece, 2x all to the power 4. So that means I have to do what's 2 to the power 4, which is 16, and then x to the power 4 is x to the 4. Okay, negative 3 to the power 0 is 1. Okay, next term, I keep my 4. Okay, what is 2x all cubed? Okay, 2 to the power 3 is 8. And I have an x cubed, and I'm keeping a negative 3. Okay, plus, okay, keeping my 6. 4x squared. Okay, negative 3 squared is positive 9. Okay, keeping my 4. 2x stays the way it is. Negative 3 to the power 3 is negative 27. Okay, last term, I have a 1. Anything to the power 0 is 1. And then 3 to the 4 is 81. Okay, finally, I can put all my terms together. So, right, again, we're just multiplying coefficients here, right? What's 1 times 16 times 1? That is 16, and I have an x to the 4. Okay, I need to do 4 times 8 times negative 3, which actually means this will change to a negative sign. Okay, and then I believe that is 96. Okay, x to the power of 3. Okay, next term, I've got 6 times 4 times 9. Let's see, that's 24 times 9, so it would be 240, take away 24, so 216 x squared. Next term, I've got 4 times 2 times negative 27, so again, this is going to be a negative term. Okay, so 27 times 8, 216 as well. And that's an x on it. Okay, and last I have 1 times 1 times 81, so that's plus 81. Okay, and I've expanded out my power 4 of that binomial. So that's how the pattern works. So again, you just need to practice the pattern, right, get used to it, and you'll be good to go. So your homework will just reflect that. So here's your practice work, page 466, number 4, 5, 8, and 10. Okay, 4, 5, and 10 are all binomial. 8 is actually kind of like the desk question that I put at the start to show how that works. Okay, thanks for watching, and I'll see you tomorrow.